Welcome everyone to Sham Discovers. Let's learn something new today. From the deepest caves to the darkest forests, bats rule the night skies, not through sight, but through sound. For centuries, their nocturnal prowess was a mystery. How could they fly at breakneck speeds, avoid obstacles, and snatch tiny insects from the air in complete darkness? The answer lies in a biological sonar system so sophisticated, it challenges the limits of our imagination. Our own sonar systems, used in submarines and medical imaging, are technological marvels. They emit sound waves, listen for echoes, and build a picture of the environment. But even the most cutting-edge human sonar pales in comparison to the bat's natural ability. Why? Because bats have evolved solutions to problems we're still grappling with. First, the sound itself. Bats produce incredibly loud, high-frequency ultrasonic calls, often exceeding 100 decibels, louder than a rock concert, right next to your ear. But humans can't hear these frequencies, which is why bats appear silent to us. Their larynx is a specialized sound engine, capable of rapid, precise sound generation. Why ultrasonic? Higher frequencies mean shorter wavelengths. And shorter wavelengths are like using a finer brush to paint a picture. They allow for the detection of much smaller objects and finer details. It's the difference between trying to feel a pebble with a giant beach ball versus a tiny marble. Many bats have elaborate nose leaves, intricate folds of skin around their nostrils. These aren't just for show, they act like parabolic dishes, focusing and directing the ultrasonic calls into a precise, narrow beam. Coupled with the tragus, a fleshy projection in their ear, they create a highly directional sound system. A bat's ears are not just receivers, they are sophisticated, independently steerable antennae. They can swivel, tilt, and even change shape, constantly adjusting to capture the faintest echoes and pinpoint their origin with astonishing accuracy. Imagine having ears that could literally point like radar dishes. As a bat flies, both it and its prey are often moving. This creates the Doppler effect. The perceived frequency of sound changes with relative motion. Human sonar struggles with this, but bats are masters. Their brains can instantly compensate for their own movement while precisely calculating the speed and direction of their target from the frequency shift of the echoes. Imagine trying to find a single grain of sand in a desert, using only echoes. This is the clutter problem for bats. Every leaf, every twig, every other bat creates an echo. Bats have evolved incredible neural filters to ignore irrelevant echoes and lock onto their specific target, even in the densest foliage. Just like our eyes have a fovea for sharp central vision, some bats have an acoustic fovea. They can rapidly sweep their narrow sound beam across a target, gathering incredibly detailed information from a small area, then widen the beam for a broader scan. This dynamic focusing is key to their unparalleled precision. Not all bats scream. Some, like the whispering bats, emit very low-intensity calls. They compensate for the weaker signal by having exceptionally sensitive hearing. This allows them to hunt prey that can detect ultrasonic sounds, giving them a stealth advantage, a silent predator in a noisy world. Imagine hundreds, even thousands, of bats echolocating in the same cave or forest. It should be an acoustic nightmare, a cacophony of overlapping signals. But bats have evolved sophisticated strategies to avoid jamming each other's sonar, often by shifting their call frequencies or timing their emissions. It's like an unspoken agreement in a bustling sonic marketplace. The true magic happens in the bat's brain. Specialized neural circuits process the incoming echoes with incredible speed and efficiency. They can calculate distance, direction, velocity, and even the texture of objects in milliseconds, far faster than any human-designed computer can process raw sonar data. Distance is determined by the time it takes for an echo to return. Bats can measure these time differences down to microseconds, 1/1,000,000th of a second. This extreme temporal precision allows them to differentiate between objects just millimeters apart, even at high speeds. It's like having a stopwatch that measures the blink of an electron. From these precise time and frequency measurements, bats construct a dynamic, real-time 3D map of their environment. They don't just see dots, they perceive shapes, sizes, and even textures. Imagine navigating a complex virtual reality environment, but with sound instead of light, and with far greater detail. This is where bats truly leave human sonar in the dust. They can discern not just the presence and location of an object, but its surface texture. A rough leaf reflects sound differently than a smooth one, and a fuzzy moth provides a distinct acoustic signature. This allows bats to identify prey and avoid obstacles with incredible nuance. A bat's echolocation isn't static, it's a dynamic, adaptive system. When searching for prey, they emit calls at a lower rate, scanning broadly. Once a target is detected, they rapidly increase their call rate, sometimes up to 200 calls per second, to get a continuous, high-resolution update, allowing them to precisely intercept their meal mid-flight. Many bats don't just emit a single frequency. They use frequency-modulated calls, sweeping through a range of frequencies within a single pulse. This broad spectrum of sound provides more information about the target, improving both range detection and target identification. It's like using multiple radio channels simultaneously to get a clearer picture. The external ear structures of bats are not passive receivers. They are highly mobile and flexible, constantly adjusting their shape and orientation. This allows bats to actively sculpt the incoming sound, enhancing specific frequencies or directionality, literally tuning their ears to the environment and the task at hand. How do bats avoid deafening themselves with their own incredibly loud calls? Just before emitting a pulse, tiny muscles in their middle ear contract, dampening their hearing. Then, as the echo returns, these muscles relax, allowing them to hear the faint reflection. It's a precise, rapid-fire self-muting system, like a natural noise-canceling headphone. The precision of bat echolocation has driven an incredible evolutionary arms race. Moths, their primary prey, have developed their own countermeasures. Some have ears that can detect bat calls, allowing them to take evasive action. Others produce their own ultrasonic clicks to jam the bat's sonar. It's a high-stakes game of hide-and-seek played with sound. The bat's sonar system is a masterclass in efficiency and adaptability. Scientists and engineers are constantly studying bats to inspire new technologies, from more precise medical imaging devices to autonomous navigation systems for robots and drones. Nature often holds the blueprint for our most advanced innovations. Imagine a drone that can navigate dense smoke or murky water with the same precision a bat navigates a cave, or medical imaging that can detect anomalies with unprecedented detail. By mimicking the bat's dynamic frequency modulation, its clutter rejection, and its sophisticated neural processing, we are slowly closing the gap on nature's genius. Ultimately, bats experience the world in a way we can barely comprehend. Their reality is a dynamic tapestry woven from sound, where echoes reveal not just presence, but texture, movement, and intention. It's a reminder that our own perception is just one sliver of the incredible spectrum of sensory experiences across the living world. The bat's echolocation system isn't just one amazing trick, it's a symphony of finely tuned adaptations working in concert: specialized vocal cords, intricate ears, a self-muting mechanism, dynamic frequency control, and a brain that performs real-time supercomputing. Each component is critical, and together, they create a sensory masterpiece. So, when we ask how bats echolocate with more precision than any sonar system, the answer is profound: they've had millions of years of evolution to perfect it. They've optimized every biological component, every neural pathway, to create a system that is not only robust and efficient but also exquisitely precise. Their world is one of echoes, a constant, high-definition sonic stream that allows them to hunt, navigate, and thrive in conditions where our most advanced technology still falters. It's a humbling reminder of the incredible ingenuity that exists just beyond the limits of our own senses. Thank you for watching. Don't forget to subscribe to Sham Discovers and turn on the notification bell for more educational videos.